Hello, welcome to this class. In this class, we'll start with ideal and real gases. We'll start with what we already know, which is Boyle's law. For a fixed mass of gas, at constant temperature, the pressure of a gas is inversely proportional to its volume. So, how do we interpret? If you consider a piston and a cylinder arrangement, then if we expand this or compress this piston at constant temperature. Now, let us keep the temperature constant. Now, what will happen if we increase the pressure? Volume will reduce, or on the other hand, if you increase the volume, pressure will increase. So, we are saying that pressure is inversely proportional to volume. Now, we are talking at constant temperature. For a constant temperature process, pressure is inversely proportional to its volume. Or we can also say, if you bring this volume here and then remove the proportionality constant, we can say PV is equal to constant, which is product of absolute pressure and volume is constant for a constant temperature process. Now, how do we write this here? If the process which we have written here, let us say it is an expansion process. If the piston has moved from state 1 to state 2, if the piston has moved from state 1 to state 2, then in a PV plot, it looks like this, a process which we call it as constant temperature process, or PV is equal to constant process looks like a hyperbola in a PV diagram. So, this comes from experiment. We should remember that it looks like this in a PV plot. Now, let us go to one more law which we know, which is Charles' law. Now, for a fixed mass of gas at constant pressure, the volume of a gas is directly proportional to its absolute temperature. Now, similarly, we have taken one more system where the gas is behind the piston or in the cylinder. Now, what we are saying, if the pressure is constant, volume of gas is directly proportional to its temperature. Now, remember, if you try to keep the pressure constant, add the heat or remove the heat, what will happen you can see. If you add the heat here, what will happen? If you try to keep the pressure constant, if you add the heat with increasing temperature, the volume also increases. Our piston starts moving to the right in order to keep the pressure constant. So, for increase in temperature, volume also increases. Or if you cool this down, the temperature drops and in turn volume also reduces. Now, let us assume an expansion process. Let us say we are heating from 1 to 2 with pressure is constant. Now, how does it look like in a PV diagram? So, it is like a constant pressure process where heat is added. So, let us say this is state 1 and this is state 2. So, it will be a constant pressure process. So, it will be a horizontal line in a PV plot. And remember, pressure is constant, which means P1 is equal to P2. So, volume is proportional to temperature can be further rewritten as volume. This temperature can come to the left, and this proportionality constant if you remove, V by T is equal to constant, which means V1 by T1 is equal to V2 by T2. Alright. Now, similarly here we had proved PV is equal to constant, which means that P1 V1 is equal to P2 V2. If temperature is constant, we can write PV is equal to constant. Now, we have seen Boyle's law, which talks about pressure is inversely proportional to volume when temperature is constant. We have seen Charles' law, where volume is proportional to temperature, while pressure is held constant. Now let us combine these two laws, combination of Boyle's law and Charles law. Now let us assume the same piston and cylinder arrangement, okay, where state 1 is somewhere here. Now we have taken PV diagram. Now state 1 is somewhere here. I am assuming state 1 here with certain pressure and volume. Let us say the piston has moved from here to here. Piston has moved from here to here, which satisfies, let us say this is intermediate state I have taken, which satisfies Boyle's law. Now what does Boyle's law states? PV is equal to constant. So that is process 1 to I. Process 1 to I is Boyle's law, which satisfies Boyle's law. PV is equal to constant. So we know how the curve in a PV diagram looks like. This will be an hyperbola. So this is I, or we can write it as PV is equal to constant, or temperature is equal to constant. Both are good. Now let us say the same gas behind the piston expands further and the piston moves from here to the right furthermore. Now let this be according to Charles law. Now let us say from I to 2 we have a constant pressure process. From I to 2 we have a constant pressure process. Constant pressure process. So we can write process I to 2 is Charles law. It satisfies Charles law, which states that volume is directly proportional to temperature, or we said that V by T is equal to constant. Okay. Now using these two laws, let us try to derive. Now that is in first process 1 to I, we can say process 1 to I, we can say P1 V1 is equal to Pi Vi, because PV is equal to constant during process 1 to I. Okay. So we can simplify for Vi because that is what will be common between 1 to I and I to 2. So Vi is equal to P1 V1 by Pi. So this is what we can write from process 1 to I. Now similarly, let us go to process 1 to 2, process I to 2. Now process I to 2, what is constant? Pressure constant, or we can say that V by T is equal to constant. I will write V by T is equal to constant. Now what is V by T is equal to constant here? Vi by Ti is equal to V2 by T2. Okay. Now let me simplify this for Vi, because we have equation 1 which is also simplified for Vi. Now Vi is equal to V2 Ti by T2. Now we have got two expressions where LHS is same. So equating 1 and 2, what we can get? Equating 1 and 2, we can say P1 V1 by Pi, P1 V1 by Pi by Pi is equal to V2 Ti by T2. Now remember this, from this process P1 V1, let me simplify this further, P1 V1 by Ti here, and let this P go here, Pi V2 and T2. Now what is Ti? Temperature is constant between 1 and I. This can be rewritten as T1 because we know that T1 is equal to Ti. So therefore we have written, because temperature is constant between 1 to I. And on the other hand, Pi can be written as P2 because, and we also know pressure between I and 2 is same. So, Pi is equal to P2. So, P2 V2 by T2. Now, what did we just prove? PV by T is equal to constant between the two imaginary process which we have considered. We have proved PV by T is equal to constant. See, since states 1 and 2 are arbitrary, and we have shown that P1 V1 by T1 is equal to P2 V2 by T2 using convenient imaginary path. Therefore, the quantity of PV by T must be constant for any process undergone by a fixed mass of perfect gas. Now, what is perfect gas, which we will have to derive now or define now? Now, what we can say is that PV by T is equal to constant. Now, what is this PV by T is equal to constant? This constant depends on mass and properties of the gas. That we will have to talk now. Now, in other words, we can say PV by T is equal to M, which is mass, and one more property which we are talking now, a characteristic gas constant. We'll talk about that little more. PV is equal to PV by T is equal to MR, or we can say PV is equal to MRT. Now, this is the equation which we are trying to derive. This we call it as ideal gas equation. Now, what is an ideal gas is our next question. So, there are assumptions which were made during derivation of this particular equation. The assumption was gas molecules are point masses. So, volume of the particular molecule is negligible compared to the container volume. Now, this is very important because while talking about real gas, we talk about why the correction is made. So, we have made an assumption during an ideal gas equation that molecular volume is negligible compared to container volume, and we have also neglected intermolecular forces. So, we have neglected intermolecular forces of attraction and repulsion. So, molecule interact only during collision. So, an ideal gas is a gas, we can say an ideal gas is a gas which obeys the equation PV is equal to MRT. So, in simple words, an ideal gas is a gas which obeys PV is equal to MRT. So, an ideal gas is a hypothetical gas that perfectly obeys the ideal gas equation PV is equal to MRT under all conditions of temperature and pressure. Now, we can talk about the same equation in different forms. Now, before that, let us try to know the units of each quantity. Now, pressure should be in Newton per meter square, volume in meter cube, mass is in kg, and this is R is characteristic gas constant, which we have to talk about, and T is absolute temperature in Kelvin. Okay. R is joule per kg Kelvin, and temperature is in Kelvin. So, pressure is absolute pressure in Newton per meter square. Volume is V is volume in meter cube. Characteristic gas constant, I said joule per kg Kelvin. Absolute temperature should be in Kelvin, and M is mass in kg. Now, you can see the equation is balanced. Meter square goes with meter square, you will have Newton meter, which is joule on the left side. Right side kg, kg cancels out. You have Kelvin, Kelvin cancelling out. So joule. So equation is balanced, which means the pressure should be substituted in Newton per meter square, volume should be in meter cube, mass should be in kg, R should be in joule per kg Kelvin, and temperature should be in Kelvin. Okay. In the next class, we will see that how this ideal gas equation can be rewritten in different forms. And we will also take up few more problems. Then later we will solve real gas problems with the introduction to real gas. Thank you.